In this section, we're going to talk about hypothesis tests for proportions. Anytime we have a claim about proportions, probabilities, or percentages, we can talk about population proportions. So just like for Chapter 7, when we created a confidence interval for a proportion, we used the normal distribution. We're going to do the same thing here for hypothesis tests. It's the same idea. We use the normal distribution to approximate the binomial distribution. This is coming from section 6.4, and we can use that standard normal to test hypotheses for proportions, just like we used the normal to create confidence intervals. Our test statistic has a formula to it. We're not going to use it. We're going to be using templates just like before. Just know that if you wanted to do it by hand, you could. And we have 3 requirements for testing a proportion. We have that simple random sample. We have a binomial distribution, essentially, with our proportion. And we have that n times p and n times q are greater than or equal to 5. So then we can use the normal to approximate the binomial. And then something to point out, the p that we're using is the assumed proportion in the null hypothesis, not our sample proportion. So that hopefully will show up when we work through the examples that we do. For now, I'm going to skip doing the critical values, mostly because the template gives it to us. I'll have the answers up here if you want to check as you work through, because I believe some of your homework questions will ask you these basic questions. Calculate the critical value. So instead of doing it in the template, you can just do one simple statement of norm.s.inv. It's an inverse norm function to calculate those critical values. So I'll have the answers up here so you can check your work. But I want to move into the hypothesis tests themselves. Here we have 1,009 consumers were asked if they are comfortable with having drones deliver their purchases. 54%, or 545 of them, responded with no. Use these results to test the claim that most consumers are comfortable with drone deliveries. So we're going to interpret most to mean more than half, or greater than 0.5. And the first step we have to do is check our requirements. So is there a simple random sample? Now, I know it doesn't say there. We're going to make that assumption. So we're going to assume that these customers that were asked were randomly sampled. So requirements, a simple random sample, we're going to assume that is true. The second requirement we need is the binomial distribution. Do we have a binomial? So a fixed number, we have 1,009 customers. They are independent. We're going to assume that one person's answer is independent of another person's answer, as it should be. We have 2 outcomes, comfortable or not, and the probability is the same. So we have a binomial distribution. And we're going to assume, in this case, since most is more than half, we're going to assume p is 0.5. Because this claim greater than 0.5, that's going to be our alternative. So if we want the claim to be our alternative greater, we need our null to be equal to. So the probability being here, 0.5. Then we look at the third requirement. We need n times p and n times q to be greater than 5. So 1,009 times 0.5. And since p is 0.5, q is 0.5, so they're equal. Multiply those out, we get 504.5, which are definitely greater than or equal to 5. So our third requirement is good. Okay, and yeah, we're making some assumptions here, but we might not be given the whole story in these scenarios. 1,009 customers, we're going to assume best intentions for the study, okay? State the hypotheses and identify the claim. So our null and alternative hypothesis, this time we're dealing with proportions. So we're going to use a p for our population parameter. When it's means, we use mu. When it's proportions, we use p. Sometimes you might see pi being used instead of p. Sometimes that's the case, but we tend to use p. And then we've already assumed 0.5 for the value for p. Our claim is that the proportion is greater than half, Most consumers are uncomfortable, so greater than half, but our alternative is always equality, so we'll have equal to there. When we do the hypothesis test, we assume the null is true. And that's coming in when we do the calculation for the test statistic. So if I flip back a page, 2 pages, we flip back 2 pages, this P right here, this P is from that null hypothesis. So we're assuming the null is true when we plug the value for P in here. Remember, the null has equality, so P equals a number. We use that number here to calculate the test statistic. Going back, we assume the null is true. Now we're going to plug in some stuff. So steps 2, 3, and 4 are in the template, but then we'll pull them back out. So I have my template here. Make it a little bit bigger so we can read it. Our alternative hypothesis is P is greater than, so we're going to make that switch, greater than. And I have 0.5 here, so I'm going to leave it. Level of significance. Well, we're not told. There's no significance level given. So what this means is you get to choose. You get to choose your alpha. And generally speaking, we want to choose either 0.1, 0.05, 0.02, or 0.01. Anything 0.1 and lower, essentially, we can pick for our significance level. But these are the common ones. 10%, 5%, 2%, 1%. I'm going to pick 0.05. That's the one I like using, so I'm just going to keep it at 0.05. So I need to change that here. Sample size, we had 1009 for our sample size and our customers. Number of successes. Now, they give us both the proportion, 0.54, and they give us the number of successes, 545. So if you put both of them in, notice it tells you that it's going to calculate the number of successes over the sample size. So it's calculating 545 divided by 1009. And see this P hat 0.5401, it's really close to our 0.54 that was given. So the template is going to use the more accurate one. That's why if you don't have the successes, you want to make sure that you delete it. But notice number of successes is a decimal number. That's awkward. We're going to put it back in. But it could be the case. It could be just a calculation error kind of thing. Or a rounding, like in this example. So we have our sample proportion, standard error, critical value 1.645. So all of our values up here in yellow check out. And now we can start pulling values from the template. So our critical value here, 1.645. Our test statistic, 2.55. Oh yeah, and this is where I remember I had a little bit of a problem, and I'm still trying to fix it, so bear with me with this one, and I'll try to explain what's going on. So this p-value, it should actually be 1 minus this value. Our p-values need to be areas in the tails. So this is giving me the area to the left instead of giving me the area to the right, which is unfortunate. I want the area to the right, but I haven't quite figured out how to correct it yet. So this is why I wanted to step through both the traditional method and the p-value method so that you understood what the tie-in between the two of them are. And in case a mistake like this comes up on the template, it would make sense when you go to plug in all the values. So I will work to see if I can correct this. In the meantime, traditional method is very straightforward. So we'll do that, and then I'll show you what's going on with that p-value that's given there. So critical value, we're using 0.05. We got our critical z-value. We got our critical value to be 1.645. Our test statistic was 2.55. And if we draw a graph, 0 here, 1.645. This area is 0.05. This is my rejection region. Also recall that 0.05 was, back in Chapter 4, our threshold for unlikely events. Chapter 4, Chapter 5, Chapter 6. So this significance level is just allowing us to adjust that threshold depending on what we want. So we don't have to stick it at 0.05 all the time. So Here we have our rejection region set up, and then our test statistic, 2.55, is going to be somewhere to the right of 1.645 because it's greater than. Since 2.55 is sitting in that rejection region, we're going to reject the null. Now let's talk about the p-value that they're throwing out at us. So the template says the p-value is 0.9946, but it really should be 1 minus that because the p-value should be this area up here. So we're talking about 0.0054 for the p-value. It should be the tiny amount to the right in the tail of our test statistic. And then if we compare that value to alpha, so now doing the p-value method, 0.0054 compared to alpha, 0.05, 2 decimal places, I've got a 0 and a 5, so the 5 is greater, which means, again, we reject the null. The p-value probability is too small, so it's unlikely. So we reject the null, and we're rejecting the null, so we're saying, nope, the null can't be true, which means we can support this claim. Remember, in the alternative we can support or we cannot support. We support it because our null hypothesis is being rejected, which means it should be the case that our alternative actually holds. So to summarize the results,